Hello everyone. This lecture will be explaining the linear recurrence and how to solve it using two methods, namely the one method using matrices and the other one using the generating function. To begin defining what a linear recurrence is. So linear recurrence is a formula that we can write as a recursion. And this recursion has to be a linear combination of like the previous elements. So for example, something like that. So this is a linear recurrence. So this is also a linear recurrence. In general, we can write it as 1, 1. So something like that. So all of these are linear recurrences. However, this, for example, is not a linear recurrence. So as you can see, this one is not a linear recurrence because it's not a linear combination. Because here this term is occurring raised to the power of 2, so this is not a linear recurrence. So in this I will be explaining like the really famous example. So this is the Fibonacci sequence. So the Fibonacci sequence is defined like this. And it has the base cases for 1, like f1 is equal to 1, and f0 is equal to 0. So you can see that the elements here are 0, 1, 1, 2, 3, 5, and so on. So if you would like to compute the Fibonacci numbers, let's say we compute them modulo some big prime, like 1,000,000,007, for example. So we can compute it in a variety of ways. So there's the complexity of n. This is just the recursion. So this is the very efficient way of doing it, just putting this recursion. There's the dynamic programming version of that, which makes it an O of n. So now I'll be explaining the third way to do that. So the third way basically makes use of matrices. So if we define this column vector, like xn, be defined as the nth Fibonacci value and n-1 here. So here we can multiply this vector times some matrix M. So we get this. We get like we try to get xn plus 1. So xn plus 1 will f. So xn plus 1, this is equal to n minus 1. Here I'll just put the value of this vector. So here, for example, if I put abstract elements like this, so here we get that fn plus 1 is equal to a fn plus b. So this comes from the definition of the matrix multiplication. And we'll get that under fn b times fn minus 1. So here, as we can see, we can put the a to be equal to 1 and the b equal to 1 by using the definition of the Fibonacci here. And here we can put this as 1 and this is equal to 0. So we end up having basically this matrix. We call that matrix M. So now we have that, so x n plus 1 equal to the matrix M times the vector x. So this leads to the conclusion that whenever we decrease this index here, we have to multiply by the matrix M, so the same number of times. So basically this is equal to this. So here we have so this xn plus 1, and here we have x1, and this m basically is a constant matrix. So here we can use a binary exponentiation, the same we explained it in the for the numbers. It's the same, so it's the same concept here, just that we now use different operand and operator. So instead, like earlier, we used to make some a multiplied by b, and we used to take back some number. So this was our operator, and we wanted to do that like n times. This time we just have a matrix M, and we make so the matrix multiplication. And we actually make the mod implicitly for all the elements during multiplication. So basically it's the same algorithm, can implement it, and then when we compute this into the power of n, we multiply it times x1, and then we get this vector. So an example of this would be we multiply by the matrix M for 3 times, and this x1, so this should be equal to x4. So here we can find that and this multiplication. So first I multiply these two matrices. Here one and this vector here is basically the 1 and 0. And this should be equal to 4 and 3. Anyway, so I'll proceed with the next matrix multiplication. So it's 3, 2, and that's like 2, and 1. As we can see here, this is the 3 and 2, which are indeed the F4 and F3 you expect. So putting this in code, we have something like that. Here it's the same power, but here instead the A was being a number, here it's a matrix. We have the exponent. Okay. So the matrix has n dimensions. Here I make an identity which has n, and then while the exponent is still greater than 0, the matrix multiplication is exactly the same power mode function we used to do, just we replaced the matrix multiplication. So every integer with a matrix, and then we make a matrix multiplication to return the R. This is how I'll be defining the vector. So a matrix, which is the vector. So the identity matrix is basically a matrix where only the diagonal is equal to 1 and the rest is equal to 0. So here I begin a matrix and I put n rows in it. And each row is basically a vector of n columns and 0 values. And here I make the diagonal to be equal to 1. Then return the function. And then we need to make the matrix multiplication. This we want the 0 matrix. Here I will make this mod. It's a global constant, and here finally I'll have this is the matrix. This is the matrix multiplication. I'll not explain it, so you can just find the definition. So this is the basic algorithm to do it. And here I just take a constant reference, so instead of copying the matrices each time, I can just take a reference and use the values. And anyway, I put the results in C right away. It doesn't matter if this is just a reference or a copy. Here we can make a matrix power as we wanted. So, so this is the matrix M that we had. And this is x1. So basically, if we want to have m to the power of n, so this should be power of m, so power of 10. So this is the matrix. So basically, here we end up having phi. And just take that. So x is like n plus 1. So the first elements n 0 times 1. Yeah. Yeah, this is the part I was confused. Make it like this, or you can also make it like this. Here xn is 1 is a vector of size 2. Just command those two lines out. Here we have it, and then we can print. Let's say we print the matrix, and the matrix to the power of n, and x1 and xn. So we can say matrix n. We print the matrices, and in the vector x1 and the vector n plus 1. These are the functions that we use to print. So we go for all the values in the row, print them. Not compiled. As you can see, so this is the matrix M. This is when we raise it to the power of 10. And this is the x1. So here it seems something went wrong. Yes, I should be using the int power and not the. So as you can see here, so this is the x1 vector, and this is the x11. Yes. And also write the dynamic programming for it. So here we can also print so the Fibonacci of 10 and Fibonacci of 11. So this should be the elements of the last vector that we're printing. As you can see, so this is the Fibonacci of 10 and Fibonacci of 11 are the elements of this vector, as you can see. So basically, this is one way to solve the linear recurrence. So what is the time complexity of that? So basically, we make O log n multiplication, like this is the number of matrix multiplications. So it's the number of times this function is called. And each time we call this, we have like k to the power 3. So in the Fibonacci, it was like our k was equal to 2. Like we see here, this definition of linear recurrence. So here, this is our k. So it's the number of terms that we see. And okay. So as we can see here, this complexity, this is the complexity of matrix multiplication. So this is the total complexity of this algorithm that computes the linear recurrence. I'll move now to a harder example. We'd like to compute this linear recurrence, or actually this one is not a linear recurrence. So it's the sum of the squares of the Fibonacci number. So basically we want to compute this. So this is not a linear recurrence, but we can still compute it because somehow we can formulate this as a linear recurrence. So the way we do this, I'll define xn to be fn squared. So here we can substitute with the definition of Fibonacci and get 2 whole squared. So this is fn minus 1 squared, fn minus 2 squared, into fn minus 1 times fn minus 2. So as we can see, this is equal to xn minus 1. This is xn minus 2. And this is 2. And this part, we call it another recurrence. Let's call it z. So n minus 1. So by this, we get that. So there's this z, and it's equal to fn times fn minus 1. Here we can substitute for the Fibonacci of n in this term. So it's like that. So fn minus 1 squared plus fn minus 1 times fn minus 2. Yeah, as we can see here, we have, so this part here is x n minus 1, and this part here is z n minus 1. So here we can basically come up with these three formulas. So Sn so Sn is equal to Sn minus 1 plus xn, and we have, so xn equal to xn minus 1 plus xn minus 2 plus 2 z minus 1, and lastly we have zn is equal to xn minus 1 plus zn minus 1. And we have our originally fn is equal to actually don't need that anymore now. So if we look at these formulas, so this we can also try to compute using, so now this is a formulated linear recurrence. We can use this to compute it using some matrix. So we define a vector Pn. So this vector has Sn, Xn, Xn minus 1, and Zn. I think we don't need other values, but we might need, we'll see. So here we also try to find some matrix. So this is V plus 1. So this vector here, this is V n plus 1. So this is equal to some 4 by 4 matrix. Here we have Sn, Xn, n minus 1, and Zn. So here we can fill like these values. So Sn plus 1, so like as we know, so each row, so this is A, B, C, and we multiplied by this column, X, Y, Z. So basically the result is like the dot product. So it's AX plus BY plus CZ. So here we have to choose like the A and B and C carefully, so we end up having the value that we want here somehow. So Sn plus 1 is equal to, so the coefficient of Sn is 1, and the coefficient of here we need actually Xn plus 1. So we might try to change this to increase it by 1. Something like that. Also here. Then I'll try again to put the values. So here we put this 1. Then now we have Xn plus 1, so it also has the coefficient 1. So here. And the rest of the numbers have coefficient 0, because they actually don't exist in this equation. Then we use this, so this Xn plus 2, this is basically Xn plus 1 plus Xn plus 2 Zn, like here, so it's the, because this is n plus 2, so we want Zn plus 1. Actually, we need also to increase this here, and here, this will be 2. So get back again to here. This 0 because it doesn't exist, and here's 1, 1, and this is the 2. And then And for the xn plus 1, it actually exists here, so we can just get it from here. Likely. And then for the zn plus 2, so this is equal to zn plus 1 plus xn plus 1. So basically, this is 1 and 1. So it's those two, so it's like that. Basically, when we have this matrix and we take it to the nth power, so we can compute this vector. It only remains to know what is the, in our case, so the v0. This v0 is the only part that we still need the Fibonacci, because we need to know the base case. So S0 is basically the sum of the terms until F0, which is 0. Then xn plus 1. What was the definition of that? So basically it's the square of Fibonacci. So the square of f of 1 is 1. And this, so xn here is the square of the 0, which is 0. And zn plus 1, and get that again here. We find that zn is fn times fn minus 1. So basically here it's f1 times f0. Is 0. Okay. So basically here we have Pn plus 1. This is equal to this matrix n raised to the power n times v0. Can try to compute that. Okay. So this is the dynamic programming part. And here we'll have the sum that we want. So I so this is the sum that we wanted then. The matrix just will change a bit. So it's 1 1 0 1 1 2 1 here. 0 1 0 1 0 1 0. And as you can see, the base vector is 0 1 0 0. This has now power 4. it works. We have here we can 11. Now we don't know which are the elements because this is the only element that we want, which is identical to here. As you can see, this is when we make the power is equal to 11, we get all the sum of squares into 11, and so on. And in the previous iteration, the previous execution, we had this for the matrix raised to the power of 10. So the first element in the resulting vector is indeed equal to the index sum of 10. So this is the result which we expected. Okay. So this was how to solve some linear recurrence using matrix exponentiation. There's also another method that's interesting. I'll just mention it briefly here. I will not explain it here. So in the example of the Fibonacci, we had this matrix 1, 1, 0. We wanted to raise this matrix to the power of n. This has to be so here we can somehow, if we get the eigenvalues of this matrix, they are the lambda 1, lambda 2, then we can have rearrangements of this matrix M. Some matrix A times the diagonal matrix and A inverse, where this A is a constant matrix and this D is a diagonal matrix, where the values are equal to this. So what is so special here about the diagonal matrix is that when we raise m to the power of n, this is basically equal to this value. This we can prove by induction. So n power n plus 1, this is equal to n power n times m, which is equal to a d power n, a inverse a d power n, a d power 1. So we end up having, so this a inverse a cancel each other, so we have d to the power n plus 1. So after we, and the diagonal matrix, when we raise it to some power, we have d to the power of n. Actually, we raise all the values to the power of n. This we can also prove in some way. So once we have this, here actually you can, so we have this value here. It means that this d power n, which is lambda 1 raised to the power n and lambda 2 raised to the power n, and so it's this guy here, or this guy here. So after we multiply by this a here and the a inverse here, we just get some linear combination of these values here. So this linear combination depends on the values in A. End up having some, let's say A1, A1, A2, this is A3. Before, okay, 4. So basically here we have this formula for f of n plus 1, or in our case it's n. So from here we can actually, if we have the eigenvalues and we manage to get these coefficients, then we have a closed formula for the Fibonacci, or actually it could be other linear recurrences. So here to support the Fibonacci sequence, we have the eigenvalues of satisfy this equation, which will happen with the two values phi and conjugate phi. The phi is the golden ratio. And the phi is equal to 1 plus square root of phi over 2. So basically, yeah, this is it. So this value is around 1.6 and 8 something. So this golden ratio, you can find that has like really a lot of, like, so let's say applications, or it's at least seen a lot in arts and nature and so on. So somehow defines some standard of beauty. So you could look it up. So basically this is the Fibonacci is actually given by this closed formula. So yeah, and I'm sorry, so the conjugate here is 5 plus 1. So here this is Fibonacci of n is given by this formula. This we can verify using induction, and also we can try it and so on. So this will also yield to all the solutions of the Fibonacci. And this method can be extended even further to other linear recurrences. And here this also shows that the Fibonacci of n, it grows exponentially with the order 5 to the power of n. So all of these are properties about the Fibonacci that we just got from like solving the Fibonacci sequence here. So this was one way to solve the Fibonacci. So it was using the matrices. The other way would be using generating functions. And by the way, this part here is called the diagonalization. We can like find a diagonal version of any matrix such that this property is satisfied. And this matrix A depends on the eigenvectors of the corresponding eigenvalues. So just to keep in mind. So the generating functions include, so we define some function as an analytic polynomial function. So we have summation or infinity. So to the all powers of x, and each one has some coefficient ai. And then we can play around with this and get like different ways to solve the these coefficients here. So for example, so we can define some, let's say f1 x. So this will be the Fibonacci numbers. So we choose the coefficients to be the Fibonacci. So basically that's it. Then we start to introduce some properties of the generating function, so we can shift all the function if we multiply by x. So basically, if we multiply this term by x, this is equal to I equals 0. It's usually nice to make this index here the same as the power of x, so I'll just shift this around a little bit. So this is starts from 1, and this is Fibonacci I minus 1. This goes to infinity. You can also multiply another time. So we have x squared times f1 from 0 to infinity I x I plus 2, which after rearranging start from I equal 2, and we have I minus 2 I infinity. So here we'll try to sum these three expressions, these two expressions. So if we make this summation, let's do it here. So here I'll just get here this one term to get out. So this expression is also equal to this. I from I equal to the same expression. And then we add a constant outside for the I equal 1 case. Basically f0 x to the power of 1. So this is square equal. Here you can see that we have the summation from I equal to Fibonacci minus 2 and I minus 1. This is times x1. Basically, this is what we have here. It comes from here. So this should be pretty clear. So when this part, we can actually use the definition of the Fibonacci or just to substitute it here. So this is I plus 2 infinity. This is the Fibonacci of I. 1. Then we notice this part is the same as f1 of x, but excluding the first two terms. F0 is to the power of 1, and then we take f capital of x minus 0 minus f1. So if we use the values, so f0 is equal to 0, f1 equal 1, and we rearrange the equation, so we end up having this expression. So this part will be equal to minus x. So basically this is the generating function of the Fibonacci. It's this expression. Actually this points out that maybe I was a bit hasty in one of those parts. So here just the eigenvalues, it's probably this is minus 1. I'm not sure. Here we have the eigenvalues. We basically come from here. 1. The determinant of this has to be equal to 0. So yeah, this part is actually correct. We come back to here. This we try to decompose into two parts. So it will be one. Now we have this expression that we can somehow decompose this using this form, such that when we add those two again, we get the same original form. So this means that v1, so this multiplied by this expression is this value, plus this multiplied by this expression, this value, into v1x, and then the denominator will be the multiplication of those, v1 into x squared A1 plus 2 times x. So here we can try to solve this. We have b1 plus b2 equal to 0. And b1 b2 plus b2 a1 equal to -1. We have a1 times a2 equal to -1. And a1 plus a2 is equal to 1. So we'll find here that the A1 and the A2 are actually the solutions. So they are again the phi and the conjugate of phi. I don't recall. So the B1. So from here we have the B1 is equal to minus B2, and then we try to substitute Knuth here. So means A1 times B2 minus B2 times A2 equal to -1. Basically, B2 is the difference between, so A1 minus A2. So we'll find this part is equal to square root of 5. So here we have B2 is equal to -1 over square root of 5, and this is equal to -5. Basically, here we have some like values for this expression. So these A's and B's, we all have them. So this can actually be written nicely. Yes. I remove now this. There's B1. So basically it's this expression, and we know from so the geometric series we have this is basically the summation from I equals 0 until infinity of the expression I equals. So here we have some interpretation for this. So basically this is 1 over square root of 5, and this is summation of phi for I times xi in this part, so it's minus here. And this is the phi conjugate times x power I. And we can combine the summations to end up having this summation. And which this exactly is the same formula that I explained in the matrix. Well, actually phi minus phi conjugate is equal to square root of phi. So basically the coefficient of the term like of x power I is this formula, which also we included earlier that it's the Fibonacci. So basically this is the formula I have for Fibonacci. While in practice I wouldn't code like this formula because it has floating point numbers. It would be a bit tricky to calculate. But if we, for example, would need the Fibonacci of some number, here we could also somehow find the phi mod some prime or so on. Basically. So here this is the 2 inverse as we know how to compute it. The square root of 5 might exist and might not depending on which prime we're using. So we might actually find some phi in the integers that shows phi satisfies this equation. So if we want the Fibonacci mod some prime, we can just find some number that satisfies this equation locally. Or we can compute it this way. So if we have this, we can basically compute the Fibonacci, otherwise we have to use the other methods like the matrix. Because they are better in terms of accuracy, as they don't use the floating point numbers. So this is all we have for today. Can also explain another example about the generating functions. I'm not sure I could go through them. This is actually one of my favorites. So we have this expression here. It is equal to this summation. So I times 2 for I. Okay. So this we define a generating function g, right? So this g is equal to I. Here we just make it a finite number, so it's infinite. So here's x for I. So here we can make an interesting operation, which is basically the derivative in the, so as we know it in calculus. Basically g dash here is equal to I times x to the power I minus 1. Basically this has to start from 1. So this is so this leads to the following conclusion. So if we multiply x times g dash of x, I for x I for n. So basically this will end up with this expression, which would be actually really close to what we want here. We just plug in like the the x to be equal to 2. But sadly we cannot do that because we still don't have an expression for the g dash. But here we can actually, so this is a geometric series, so we have this is equal to x plus 1 and over minus 1. So g dash here is equal to the derivative of this expression will be equal to 1 square, the derivative of the upper part is the lower part, is the derivative of the lower part times the upper part. So this is the derivative, so if we multiply this expression times x, then we put x equal to, then we get the value an. Basically this is what we will do here, so we get that an equal to, so this 2 is the x we multiply, and then we try n plus 1 times 2 for n. This is 2 minus 1, which is 1, so we don't do anything. This is 2 for n plus 1. And this plus 1, and this is basically 2 minus 1 squared, which is 1. We have this 1. We end up having this expression is a closed formula for this summation here. So this was another example to show how we could use the generating function. So here we use, for example, the derivative operator. You can still yield some interesting results. Sometimes I even encountered like using like derivatives and shifting here as like when we multiply by x, and like some other operations, for example, and something like this. Something like that would involve the generating function that has some shifting, but also some derivative. So we will end up having some differential equation for the generating function in this expression. And then we can try to solve this differential equation. If we're lucky, that has a nice elementary solution, and from that we can get a general expression for this. Otherwise, we might not be able to. I mean, using the generating function. But it's a really nice tool, and it sometimes it comes in like really handy in solving some really hard formulas. So, all right, so that's it for today. I hope you enjoyed it, and thanks for watching.